All right, the next talk is by Ethan Crumlin. So he's from the Advanced Light Source at the Lawrence Berkeley National Labs. Ethan is a staff scientist there and is also associated with the Chemical Sciences Division. His research focuses on revealing the chemical and electrical properties of interfaces under real conditions for energy, water, geological, and biological systems. So the title of his talk is Using Ambient Pressure XPS to Probe the Solid Gas and Solid Liquid Interface under in situ and operando conditions. Okay, thank you, Ethan.
Great, thank you all very much. I'm really excited to be here and talk with you, and I really want to thank the organizers for inviting me to share the kind of work that we've been doing. I'd like to usually start off with this type of slide because this is images from around the world and traveling and all the things that many of us have interacted with in life, and the dynamic richness that we all can experience, and especially as we come through the last year and a half, look to explore and engage in again. But one of the things that these all have in common is the fact that they are interfaces. Life is a compilation of interfaces, and they're between solids, liquids, gases. And these interfaces are parts that are really behaving with regards to our aspects of life and also our greatest challenges. So if we want to be thinking about how we can clean our air, and we want to be taking a picture next to a real part of the city instead of a picture of a city, we need to overcome some of these challenges. Clean water, desalination, purification. These are some major challenges, but also understanding of fundamental and large-scale processes like geological processes. These interfaces are really at the crux of this. And then also one of the things that I focus a lot of my work on has been with regards to electrochemical systems or catalysis systems. But all of these things, interfaces are the core. This is what links them all together. And so understanding these interfaces is important. And we also can humanize interfaces very well by even things such as love, right? And connections with people. And so this is me with my son when he was born, and now he's approaching almost a year at this point. So interfaces are with us in every aspect of life. So how do I think of an interface? And so this is an example of what that interface would look like. And if I start to deconstruct this interface, I see four main components: structure, products, profile of potentials, and interfacial chemistry. And if we want to have the specific techniques that can help you identify various aspects of these deconstructions, we've heard some of them today, especially with regards to the surface structure. What I'm going to talk to you about is how we can focus on understanding potential profile and interfacial chemistry using a technique called ambient pressure X-ray photoelectron spectroscopy. So XPS. XPS, as just a really quick refresher, is where we take an X-ray. This comes in, it kicks out an electron. That electron has information in it that we are going to be looking at and detecting in a hemispherical analyzer. And this is what it looks like a little bit more schematically in terms of the hardware. X-ray comes into a sample, that photoelectron comes in and gets detected. And from that detection in that photoelectron that we're collecting, we get kind of a lot of richness of information. So the information we can get is elemental. So which element of the periodic table are we looking at? So chemistry, oxygen, nitrogen, metals. And we can also start to get, so you can see here, we're seeing the difference between carbon and nitrogen. We can also tell the difference of chemistry. So what is the bond environment? So for example, this is carbon fluoride, this is carbon oxygen with carbon. They all have different kind of chemical signatures based off of their chemical environment. It's also quantitative. So, and in a somewhat intuitive fashion. So you can see that in this one, all of these carbon species, there's one of each. And so you see unity with regards to the quantity that's present. Here you see that there's two of the hydrogen carbon bonds and one of the carbon oxygen bonds, and you see that there's 2-to-1 ratio. So it provides this quantitative aspect very clearly. So we can get elemental information, chemical information, and then another really big part is electrical information. And so this is probably one of the most underutilized aspects of this technique, but we'll talk about it briefly as well. So the minimum challenge is, how do you actually do a technique where you want to look at a real interface But the technique is using this kind of looking at the photoelectron, and the environment typically of XPS is in a vacuum environment that's lower than space. So it's ultra high vacuum is traditionally the operating system. But if we want to be able to look at these real systems while these conditions are operating to understand how they work, what their function, how do we make them better, we have to kind of adapt to the technique and modify it. So how do we do that? And so this again is a structure of a traditional XPS system. So X-ray comes in, photoelectron comes out, and that allows you to effectively get the binding energy or kinetic energy scale of your solid sample that you'd be looking at. That's how this technique originated. However, with this analyzer, what we can do is we can add differential pumping to the analyzer and some electrostatic lenses to this analyzer so that we can effectively have a higher pressure here where our sample is and still collect the signal. So this is where the ambient pressure comes into XPS, differential pumping and these electron optics. Now we can start to collect the gas phase and solid, the gas-solid interface together simultaneously. This kind of version of this technique was started in the early part of the 2000s, and it started between Berkeley at the Advanced Light Source and Bessie in Germany. And since then, over this time, almost every synchrotron facility in the world has one or is planning on one, and some are even planning on multiple. And at ALS, we have quite a few beamlines that are actually dedicated to this technique. And so in the United States, what we have with regards to the various facilities, the bottom three, so SLAC, ALS, and NSLS2, these also have the ambient pressure XPS facilities available to as a resource. So what I want to do is quickly walk through some examples of how we look at solid gas interfaces and how this can be thought about. And we're going to kind of quickly touch upon the influence of temperature, molecular absorption, and reactions. And so for this first example, what I just want to show is what does it look like inside one of these chambers, this ambient pressure XPS, and this is what it is. It's a large kind of chamber. This whole volume will be filled with the gas that we're interested in exposing to our sample. We see here is a sample on a holder. This particular one is actually set up for an electrochemical system at a solid gas interface. So we can even provide electrical stimulus to the sample. We have an X-ray transparent window, so X-rays can come through but hold the pressure gradient. And then right through here is the analyzer cone, where there's a very small aperture where the gas is coming through, but also most importantly, the photoelectrons that are being excited. So this is the, as the sample is moving in place, it'll get in line with the X-rays and the analyzer. To see the influence of temperature, what I want to just show you is an example of how a lanthanum strontium cobaltite, so this is used in high temperature solid oxide fuel cells as a cathode. This material between a bulk, just pellet of particles, and thin films should show different activities. And so one of the aspects of the study is what is actually happening to dictate the difference of performance between a bulk to a thin film. So looking at this for really the first time in this ambient pressure environment, we brought this into an ambient pressure XPS, and we would just start off with collecting XPS. This is the traditional XPS spectra you would see from a lab-based system largely. You would look at it, you'd see the carbon 1s, the carbon would be on everything that you naturally bring in. And so this is not really a surprise, but what's kind of interesting is now we can add environments, we can change the environment. So we're going to add a gas environment, so we're gonna add oxygen. So we're gonna go from this UHV environment to this 10⁻³ atmosphere environment. So very high pressures of oxygen in comparison to what's there before. And we don't see any change because we're at room temperature, but now we can even start to heat. And when we heat, we can see that the carbon even burns off. It just decomposes and goes away. So carbon is even in this particular case removed from the analysis. We don't even have to worry about it. Then we look at the other aspects with regards to the other elements within the sample. So we see strontium, for example, and we compare the strontium signal from the film to the pellet. We see that the pellet, as we increase the temperature, changes very little. However, we see just from the high level standpoint of how the spectra, let's just take the shape of these curves. As they change as you increase temperature, we see that there's a significant increase in quantity of strontium within the thin film. So this means we effectively are seeing a large amount of enrichment or segregation of strontium at the surface, especially in comparison to that of the bulk pellet. So the thin film has this property of enhancing and enrichment and segregation that's there. We can also see properties changing with the oxygen 1s between the thin film and the pellet, how a surface species is decomposing while the lattice is getting much larger and more prominent. When we bring all this together, it makes it very clear to us how much enrichment of the strontium is taking place on the thin film. So this gets us to see how environmental conditions between gases and temperature can modify significantly the samples that we're looking at. And this gives us a kind of a high level view of what's there. When I was looking through the literature again to remind myself of what's happened in this field to geological systems, there's actually been very light touches. I think there's a huge amount of growth that can be done to expose this technique to this community. But this is where one of the first works had started, and this involved Gordon Brown from Stanford. And what they were looking at is how water interacts with surfaces. So how water absorbs, and seeing on an MgO film, how does water behave? And so we can see they're doing isobar pressures as a function of different temperatures. This changes the relative humidity, but they're able to see the transformation of that water to various hydroxides, as well as when you can get some form of water stabilizing in the molecular form on the surface. So the relationship between the hydroxylation and the water formulation, they're able to see in an isotherm and isobar fashion. Here is another example on a different system. This is lanthanum cobaltite, but here we're showing more clearly the type of spectra you might be able to observe more clearly. This is collecting the oxygen 1s, the carbon 1s, the lanthanum, the cobalt. So we're getting all the elements of this oxide. We're changing the temperature. We're keeping a constant humidity in the background, or changing the humidity depending on how the temperature is there and the pressure that's there. And we're able to see how the different water species, and in some cases carbon, is interacting with these surfaces. So we're able to get really, for the first time, this really clear insight in terms of what is going on to the surfaces and the interfaces under these active environments. This allows you to start to really break down into several different things. Being at a synchrotron allows you to change the photon energy. If you can change the photon energy, that allows you to change the sensitivity, the depth sensitivity you're probing. So between 1000 EV to 730 EV, we're probing deeper at the 1000 than the 700. So we're seeing more surface sensitive at the lower energies. So therefore we can tell in a quantitative way what is something that is more surface from what is something more beneath or below or bulk or buried. And so we can see that the surface water and hydroxide are tuning as we go to more shallow, and we're as we normalize to that of the bulk. The fittings here are able to help to really clarify the type of chemical changes that are taking place as we are making these changes to the sample. But we're also, again, getting this electrical sensitivity because we're seeing some shift to the gas phase of the water feature that's here. What that is actually telling us is how the work function of the sample interface is changing. And this is something we can get directly from the electrical sensitivity that this technique provides us. And so if we bring all of this kind of picture together, what's happening on the surface, we can start to make a really clear picture of how the surface of this lanthanum carbonate, cobaltite, is changing when you expose it to water, and understand the relationship with temperature or convert it to a relative humidity to when you're getting the maximizations of certain species and when they're converting and changing. I want to show one last example with regard to the solid gas interface interaction. And this is with how we can see reactions taking place. So not just surface kind of absorption or some small molecular changes, but large changes as well. So here we're going to take lithium, we're going to clean it very well, we're going to expose it to different gases. And so we've already done the analysis, and we're able to start to quantify the different types of chemical species and their relative locations to each other on the sample. So when we expose lithium to carbon dioxide, we can see the different lithium oxides, peroxides, and carbonates that are forming. We can expose it to oxygen and see again how it changes the interface during this exposure. Same with nitrogen, same with water. And so all of these different chemical species create very different interfaces on the surface. If we look at the spectra more specifically, we can see the growth of this carbonate happen as a function of time. If we plot all of the data as a function of time, this is where we can get dynamic kinetic information. We can collect it as a function of time for the different pressures we're doing, so lower pressures or higher pressures. And then that allows us to break down where are potentially reaction controlled regimes from diffusion controlled regimes. So this gives us the idea of nucleation and growth dynamics with regards to these transformations of interfacial properties. And then from this, we can start to extract different reaction mechanisms that are controlling the types of growth and the behavior and properties with regards to these interactions. So what I want to do now is transition to how we look at solid liquid or solid solid interfaces. These examples will focus on the solid liquid, but they are transferable to solid solid interfaces as well. That means we're essentially looking at a buried interface. So how do we look at a buried interface? And this comes by changing the energy again. So instead of going from the soft X-ray the solid gas was at, we want to go to the harder, tender X-rays. And so for this, we're going to have an example where we have an overlayer of carbon, and we're going to look at a 1 nanometer iron interlayer. If we start to increase the photon energy and go into the tender regime, we see that as we go to the 2 to 4,000, 6,000 EV, we can start to probe that iron interlayer at energies that are between the 2 to 6,000 EV. So the higher energies allow us to probe deeper. So if we go from soft X-ray to tender X-rays, this now allows us to even start having these condensed phases. So for example, liquids. And if we can operate at 20 torr pressures, 20 torr is a great pressure because at room temperature, water is in the liquid vapor phase. So we can actually start looking at solid liquid interfaces as well. So this allows us to look at solid liquid gas interface all simultaneously. If you can form a solid liquid interface, we can even start applying potentials and look at how these potential changes are taking place. And so now we can apply this to looking at interfaces more explicitly. This is what it looks like and how we set up some of these types of interfaces. This is what we call a kind of a dip and pull technique. We literally will have a beaker of our liquid that we're interested in looking at. This whole chamber will be saturated with water vapor at this point. So it's 100% humidified. As long as we get a wetting interaction, we'll dip down, pull up. As long as it wets on terms of, we can form a very thin film that's around 10 to 30 nanometers in thickness of that condensed phase. And long as it's continuous, we're able to do electrochemical reactions. And this is an example of that electrochemical reaction. We've already did the dip and pull. We have a very thin film of that water layer that's there. Here we're doing a water splitting reaction. So we're seeing how this platinum electrode is changing its interfacial properties under these different environments, not just from a liquid, not with changing just the electrolyte, but also with applied potential. So we can kind of pull all of this together. And this is challenging experiments. Things do not always go as well as planned. So these are risky and challenging experiments, but when you figure them out, it's pretty exciting and rewarding. So just an example of how to contextualize this, visualize what's happening. What I want to show you is how we can really apply this technique. So the main thing I want you to take away from this is an electrochemical cyclic photometry plot. What essentially this means is we're changing the voltage and current, and we're trying to drive a reaction. As we change the electrolyte between potassium fluoride, let's just say for the most part, nothing chemically is happening. But when we add bromide to the system, we see a very strong current. So that means something is being promoted at a much lower potential. So let's look at the differences between these two. So we've done the dip and pull. We're going to start at -1 volt. We're now probing through about a 30 nanometer thin film of water. We're seeing the solid of the gold electrode. We're seeing the vapor phase, the liquid of the electrolyte, and also the fluorine 1s from the electrolyte. When we start to continue to step up in potential, we're grounding our gold so it stays steady. Now we see again the electrical sensitivity. We're seeing a 1-to-1 shift of our electrolyte. That means we have a very electrochemically active location. We're applying these potentials. We're going up, we're coming back down, and we see this really nice reverse C motion. So great potential control, and this is giving you very good clarity of the potential control and the chemical sensitivity of what we're seeing. But not too many things interesting is happening from the chemical standpoint of the interface, pretty static. When we add the bromide, so where something interesting happens, let's do the same thing. We're going to collect everything the same way. We'll even collect the bromide. Even in this case, the sensitivity is not so high. even with 1 molar in there, but we'll collect it anyways. Again, all the same properties essentially happening with potential control as we're going up, and now we're just before something active happens. When we get to something active, where we get to the 0.6, we see dramatic changes to the spectra that's taking place. So now you can see very clearly how we're learning something about the interface at the solid liquid interface simultaneously with this driving. So the bromide comes really flat out in a very clear way, and we see multiple chemistries of the gold. So what is happening? If we visualize this, we're kind of have a very benign system in the beginning at -1 volt. Once we get to 0.4 volts, and I magnify the bromide 3D, we can see there's actually something starting to happen. We're forcing a specific absorption between these ions and the gold. And then once we get to the 0.6 with the bromide, we're actually driving dissolution, electrochemical dissolution of the gold bromide into solution. And we can even see how it plates on our counter electrode. So now you can see an interfacial reaction driving the species in a very active way. So we can see interfaces evolve in these dynamic processes. And so I'm going to skip through this one, but essentially this is looking at the platinum electrode doing water splitting, where we can quantify the different thicknesses of this layer as it's evolving and get a clear picture of what is happening as it's all changing spectroscopically. And what I want to do is go quickly to the electrochemical double layer. We can sense potentials. If we use this technique and we create different thicknesses of the electrochemical double layer, effectively, we can now use the potential sensitivity to probe this. We'll do this by effectively looking at the change of the peak shape. If you have everything grounded and you're at the potential zero charge, all the species you get will sum up to give you a large, sharp peak. But if you have a distribution across that, what you're going to get is actually a broad fat peak. So the width of that peak can give us the potential information, the potential distribution information. So we're going to do this by looking at the oxygen S, and then we put in a probing molecule, pyrazine, and we'll look at the width change of the spectra. And when we do this, we can see that there's a minimization at one potential, and then we get farther wider as we go away from it. The minimization is occurring at the potential zero charge. So now we can see this spectroscopically, and then we can also fit the shape profiles of this to extract out the potential distribution. And we can really establish that in these kind of dilute regimes, we're seeing this exponential drop, which is consistent with the Gooey-Chapman-Stern model of these solid liquid interfaces. And this is something we can really directly probe very clearly and well. So with this, I hope that I've showed with you the ability of probing chemistries and potentials across different interfaces between solid gas, solid liquid interfaces in very clear and exciting ways. And then just quickly, some of the future directions, opportunities we see. We're scoping out new beam lines to do this, and we're looking for partners to do this, to upgrade, to make something that will converge between soft to tender X-rays, so we can do all of these things on one beam line, and also new end station modalities and data collection aspects to look at kinetics and dynamics, combining structure of electronic structure and chemistry with also physical structure and chemistry. And so this is, I think, an important aspect of its evolution. I think one thing to keep in mind is the investment in new analysis tools. So we're also working on trying to pioneer how to make this more approachable for other people to come to this community and use these techniques. And so how do you go between predicting, we're predicting now spectra and the chemical processes from that match with our experimental data. And with this, we can actually predict the time evolutions or changes in ways that we couldn't do spectroscopically right now, or drives new ways of doing data collection. And then we can fill in a whole phase diagram once we understand the right chemistry and physics. And then lastly is an investment in people. This technique has rapidly been growing since inception, but it's been, you can see here, dominated by a lot of the catalysis, more traditional surface science. But I think there's many more fields, including this one, that would really benefit from this type of science. And we need to invest in the people to use these techniques, master them, and really excite and do well with them. And so with that, I just want to thank the many group members and colleagues that I've partnered with to do this work and various funding sources. And thank all of you, and welcome to take any questions. Thank you.
Thank you, Ethan, for a beautiful talk. There is a question from Sang-Soo Lee. Okay, let me see. So, do you often use or see X-ray induced electrochemistry
Yeah, great question. Yeah, so most of the things that we have done, we do not see. So essentially, I say that as beam damage, right? And so we do a lot of testing for that to see if we do see any of the influence, and we have not recorded any for our type of experiments. Most of ours are on. We have some that are on bending magnets, so this is a little bit more safer. When you do this on undulators, often this is something you have to be even more aware of and cognizant of. And so that one, different collection schemes sometimes have to be done with regards to opening the beam or rastering on the sample. And so these are things we do look at in detail in advance and prepare to collect properly. So we make sure we don't get that influence. Great question.
I have a quick question, Ethan.
Yeah.
So for your dip and pull experiment, so when you pull the solid or whatever the interface out of the fluid, so isn't the interface composition going to change because of the evaporation losses of water or whatever the fluid phase?
Yeah, great question. So our whole chamber is actually at the equilibrium vapor pressure. So it's a whole 100% humidity. So it's actually an equal balance that's there. And so it doesn't have a larger evaporation rate than any other type of surface that's on the system. It's actually more in equilibrium and can be pretty stabilized, I would say.
Right. Thank you, Ethan.
Thank you.
Right. So